Okay, the key will be posted a little bit later. Yeah.
When is your birthday? Give us a birthday gift. When is your birthday?
Give us a birthday.
Whose birthday is coming up? Get some free points.
When's your birthday?
November 16th. That'll be a lit day. It's a Saturday.
Okay, UVVis spectroscopy. We have a carrot and we have a UVVis spectrometer. Similar size to like an IR. Okay, it has a light source. If you ever see one. Okay, that's page 1. I think black and white will be okay. I'll just do this here. Everybody got the handout? Yeah?
Yes.
Okay, example of a UVVis spectrum. Here we go. Typical UVVis. Compared to IR, well, it's a lot simpler. Okay? Here we have wavelength. And by the way, we're dealing with ultraviolet light and visible light. UVVis. IR deals with IR light. Okay. We have wavelength of light. In IR, we plot wave number. In UVVis, we actually plot wavelength. This is going to be absorbance. Okay, just like IR, basically absorbance or transmission. With IR, the peaks come down. With UV, typically they go up. Kind of standard. Now, in IR, you get a whole bunch of peaks. Fingerprint, lots of peaks. UVVis, much simpler profile. We just have a scan here of the wavelength. And as you scan the wavelengths, we get absorbance. And then the absorbance tails off. And when we get over here to 260, it's no longer absorbing at all. This is a UVVis for butadiene. One key piece of information we get is the lambda max. The lambda max is the wavelength of greatest absorption. Lambda being wavelength, maximum absorption. Well, it's not absorbing any at 300, very little at 260. Where's the maximum absorption? Right there. That's absorption. That comes down to what? Just below 220. Well, the answer is 217. And that 217 can become a physical constant, just like a boiling point or a refractive index. This compound absorbs mostly, or most intensely, at 217 nanometers. Wavelength in nanometers. Does it make sense that this should be nanometers? Why? Why does that make sense that should be nanometers? Because what? Because typical wavelengths in the ultraviolet range are in nanometers. Okay? What's typical wavelengths in IR? Centimeters. Yeah, but it's centimeters, and then you do an inverse to get the wave number. Okay? Which is longer, centimeters or nanometers?
Centimeters.
Centimeters are longer. So is IR weaker energy or higher energy? Longer wavelength, weaker energy. UV is higher energy, shorter wavelength, and it's actually nanometers. And we don't plot reciprocal of this. We plot actual, just pure wavelength. Okay? But what I just mentioned is your summary of your electromagnetic spectrum. And every time we do spectroscopy, I show you this. Okay? Right? We have different... the one in the IR handout was a little bit different than this one, I think. But you have high energy... would be this end, high frequency, high energy, right? Gamma rays, X-rays. UVVis. Then we get even weaker, we go to IR. Microwave and radio would be even weaker. Long waves, radio waves, long waves. UVVis, these two types of electromagnetic radiation are coupled to give one type of spectroscopy called UVVis. Typical UV wavelengths would be, I mean, you could quote it in centimeters. You could quote any number, any unit. But nanometers, what is that? 2 to 0? So what's that? 10 to the 1? Well, 10 to the 1 is like 10. 10 nanometers would be UV. What would a million nanometers be? That would be something like this. A million would be 10 to the 6, right? A million nanometers would be microwave to radio. Okay? Just, you should be able to orient yourself to that. Typically, when we talk about UVVis, we quoted the nanometers. Where IR, this is typically done in centimeters. You could do it again in any. Okay. Typically, though, your UV is about 200 to 400 nanometers. This is your practical UV that you typically scan. When you get above 400, you're then moving into the visible. Visible is about 400 to 800 nanometers. Longer wavelength because visible is lower in energy than UV. It's the UV of the sun that's most harmful, not the visible light from the sun. I thought he said it. Must say it later. Why it doesn't say it there. If you get below 200, that's called the vacuum UV range. It must say it later somewhere, unless I took something out. Okay, next. All right, how do we get absorptions? What's the process? What's going on when the molecule absorbs light here, the UV light? By the way, does this compound absorb any, based on this UVVis spectrum, does it absorb any visible light?
No.
Well, you might say, well, it's not shown, but it's not shown because there's no absorbance. All the absorbance is here. And what range is this, UV or Vis?
UV.
UVis. UV. Vis doesn't start until
400.
400. There's no absorbance out here. That's implied because it's not here. We'll state this later, but any idea what color this compound is? Purple?
Wait, let's figure. Yeah.
What color is this compound?
Is that sort of the light? It's ultraviolet range,
Okay. Anybody have a gander of what color this compound is? Okay. Maybe we'll be able to answer that by 10:50. Okay. Let's work towards that. Okay. Why does the compound absorb? Well, it's due to electrons being excited. Electron excitation. A lot of times UVVis is called electronic spectrum. Electronic spectrum. Why does a compound absorb IR? Frequencies. Okay, Bond is sitting here minding his own business. Throw me some IR. I absorb it. What's the physical phenomenon? I mean, you have to go to physics, but it's like two waves coming together, really. And they build upon each other and create a bigger. What you throw is a frequency, what this is a frequency, and they can build upon each other, and the bond can take on the energy. Okay? But where in that do we say the electrons are excited? Nowhere. I never heard that term. In UVVis, the electrons are excited. That's the main thing that's going on here. Okay? But we can have different types of electrons. And where are they excited to? This is where you really need molecular orbital theory. And I don't think you guys did any EMO in Gen Chem. Yeah, I think I've asked you that before. When I took Gen Chem, we did MO, and we were able to discuss. Y'all did a little UVVis in Gen Chem?
Yes, just a little.
Yeah.
Did you talk about the electrons' excitation or anything?
Yeah, a little bit.
Where were they excited to?
The next energy level.
Okay.
Jump.
What energy level? Okay, here's the compound, yeah? The electrons are excited where?
Oh, no.
We didn't.
No, we didn't talk about
We just had like a graph and it said it jumped up to the next energy level. That's all we really said. They didn't talk about compound specifically. Like bonds.
What energy level are you talking about then?
that. I guess that's
Yeah, I guess, orbital wise, we didn't talk about what happened in the compound.
Just do a bunch of lines
Okay,
and arrows.
I mean, this has two p orbitals, electron, overlap to make pi bond, two p orbitals, electron, making pi bond. You have some hybrids, so interacting, make,
We didn't go into that much detail.
um,
She literally, like, we drew lines and it said it would go up to the next energy level. That's all we really said.
okay, but what you're really talking about is you don't get different energy levels unless you do MO, molecular orbital theory. Okay, here we go. You have different types of electrons that can be excited. What different types of electrons can you? You can have lone pairs. You could have bonding pairs. That right there's two different types. Bonding pairs, though, you can have bonds that are in sigma bonds, or you can have electrons that are in pi bonds. So the electrons can be differently categorized. Which is going to be the easiest to excite? Well, we're excited to, but the easiest to excite are your non-bonding electrons, your lone pairs. So they're not in a bond. Okay. If you talk about MO theory, you have molecular orbitals. Sigma electrons in a molecular orbital, these can be excited to a sigma star. Sigma star would be the sort of anti-bonding molecular orbital. Pi electrons can be excited to, well, different places. Pi star, sigma star. You've got basically different levels. Electrons can be sigma bonded, pi bonded, or non-bonding. This should make sense. Which electrons are more stable? Those in a sigma bond, pi bond, or lone pairs? Those in sigma bonds are more stable. So that should make sense. But then you have your anti-bonding orbitals. When we looked at hybridization, did we ever talk about anti-bonding orbitals? We never did. That's because this comes in when you discuss a MO theory. And there's a lot of mathematics here. And there's some people that all they deal with is MO theory. Okay, the electrons can be excited. This just shows different possible transitions. Here we go. Each one of these transitions requires a different amount of energy. Which one of these 6 up here requires the least energy? The first one. Because the energy is, boom, the energy gap is small. What is this one? N, meaning non-bonding. This is a lone pair being excited to a pi star orbital. That's the easiest. Which one's most difficult? The one over here on the end. It's more difficult to excite sigma bonded electrons. Those are held tighter. it turns out that most all of these, the energy that's required here or here, all that energy corresponds to UVVis types of energy. If you throw IR at this compound, that's not enough energy to do any of this. The pi to pi star is the one that's most often talked about because it tends to be the most intense, and that's usually the most important. And if we look back at the UVVis of butadiene, the lambda max is most likely due to the pi to pi star transition. Okay, here's where it says vacuum UV. Okay. The end of pi star is the most difficult. No, I'm sorry. It's the easiest. The sigma to sigma star is the most difficult. So is this going to be higher wavelength, longer wavelength, or shorter wavelength to correspond to this energy? You need more energy, so that's going to be shorter wavelength. Yes. So is that going to be more towards the 200 N or the 800 N?
200.
Obviously 200. Well, guess what? It turns out that this is actually even shorter than 200. To get just single bonds to absorb UV, you got to get down below 200, like in the 100 range. But usually when we do UV, we start at 200.
You always don't see something.
Look at this. You see how the absorbance is there? I mean, this probably the compound absorbed over here in the hundreds. Why didn't we show this?
Because it's not UV.
It's because practically this is very difficult because there's something else that absorbs over here. Oxygen. And if you try to run this over here, you'll just get a lot of absorbance. It actually will look like this because there's lots of oxygen that will just absorb. If you want to get data over here, you have to do it under vacuum. That's why below 200 is often called vacuum UV. Get rid of the oxygen. But the pi to pi star is easier. Since it's easier, it's going to be higher or longer wavelength. Pi to pi star is never in the vacuum. It's going to be more in the UV and the vis, standard UV vis, and very often into the visible. Again, that being the energy that's needed to do these transitions. Okay, here's a UV vis of... Question?
Why is the pi star most intense?
Well, I really didn't answer yet. We just made a statement. Pi to pi star tends to be most intense. Why? I don't know that I can answer. I have to think about it. Do I know? It's typically just a statement we make. I don't know that I have an answer. There's something that probably can be answered. Why does a carbonyl tend to be intense where something like an sp3CH tends to be a little weaker? Maybe that's a reason for that. The carbonyl is more polar, and the more polar, the more it absorbs it. Throw it to me. If I'm polar, boom, I take it all. I want it all. I absorb a lot. And so that's the answer to that. There's probably some straightforward answer to why pi to pi star is the most intense. I'm just not sure I can tell you. Again, if I heard it, I'd say, oh yeah, that's right. I'm just forgetting it. But I may not know. Okay, here's a UV vis of this compound, more of a complex, I don't know any common name for it, but there we go. Whoever's showing this is showing, here we go. What's the lambda max, approximately? Well, 240, right? Right here, here's your lambda max. Somebody's playing trick on me. Lambda max right there, if we bring this down, it's about what? Well, the computer or somebody has told us that's 240. All right, you can get your ruler out. That's the point of maximum absorbance. All right, this is absorbance typically. They can be plotted in various units, logs of something. As we scan, lots of absorbance tails off. Right here we get sort of this little ridge. It's almost like something else is going on. This has been ascribed to pi star, which we said is usually most intense, so it makes sense. This has been described to n to pi star. You got to have lone pairs to do this. Does this compound have any lone pairs? Yeah, right here. So this is where the non-binding electrons are being excited to a pi star, and that occurs more like 300, okay? Which is easier to do? Well, based on your numbers, it takes less energy to do this, because that's less energy than this, longer wavelength. Does that make sense? Yes. Lone pairs are easier to excite than bonding pairs. So that sort of makes sense. But this is it. Again, pretty simplistic. You get a lambda max out of this. Do we have any absorbance in the visible?
No.
Apparently not.
Not that.
I'll go ahead and give you the answer. What color does this compound look like? Colorless. Like water or ethanol. Colorless. Why? To be colored, we're going to say it on the next page or two, you have to absorb in the visible. Why is that wall blue? There's some pigment in the paint that is absorbing visible light. If you don't absorb visible light, you will be colorless. This compound is not absorbing visible light. Colorless. Make sense? Okay. I think we'll go to the right. Yeah. Go to the right. Here's beta carotene. What do you know? How would you describe this compound? It's a polyene. Conjugated polyene, yeah? Look at all those. That's 11 double bonds if you haven't counted them already. All conjugated. All right? Where do you find beta carotene? In the carrot. That's why the carrot's on the front. All right? Here's a UVVis of beta carotene. What do you notice here? What's the lambda max right there? And that is what? About 440? You see it? About 440? So the maximum absorbance here is in what region? UV or visible? This absorbs heavily in the visible. It's going to be colored. What color is beta carotene? Orange. Orange. Why is it orange? Well, it absorbs in the visible, but why orange and not green or something? We'll look at that. But here's a question before we do that. Why is the lambda max shifted towards longer wavelength here compared to the other two examples? The answer is extended conjugation. Again, this is most likely due to the pi to pi star transition. It's usually your most intense. Okay? So we talk about pi electrons. The pi electrons are very unique here in that lots are conjugated. That leads to general stability. But why? What's going on here? And look at the next. This explains it with two different compounds. Let's go back to just two simple compounds. Ethene. Ethene would just be that, yeah? 1,3-butadiene, you don't really need the 1,3 because all you can do for butadiene is that. Pi bond, now we have conjugated. When you have, the more conjugation you have, the more narrow the gap is between your here and here, with these being ground state MOs, these being excited state. Typically, these have electrons in them, and then we excite here when we get the absorbance. Yeah? The gap is more narrow or smaller, the more conjugation you have. By the way, what do you call this guy here and that guy here? This is the one that is typically the highest energy orbital that contains electrons. What do you call this? You ever heard this? HOMO? HOMO? Highest occupied molecular orbital. What do you call this guy? LUMO. Where have you heard these terms at? Okay. Yeah. This is your HOMO, your highest occupied molecular orbital. The electron is excited from the HOMO to the LUMO. Okay? So now we can use terminology. The gap between your HOMO and LUMO is smaller with the more conjugation you have. Okay? So, is it going to be easier to do this or more difficult once it gets smaller?
Easier.
Less energy needed, so that's easier. Wavelength that's required to do this will be
What's the U?
unoccupied.
Okay.
Lowest unoccupied molecular orbital. Less energy needed to make the transition. Thus the wavelength is going to go longer. Right? Well, imagine that scenario with 11 double bonds conjugated. The gap between the HOMO and LUMO of beta-carotene is relatively small. It means you don't need much energy to do the... If you don't need much energy, your longer wavelength light will do it. By the way, everything's quantized. And only that light will do it. Now you could say, well, why doesn't the higher energy light also do it? That's because everything in science is typically quantized, right? It has to be the exact. Okay? Higher energy light ain't going to do it. This has to do with conjugation. Okay. Questions about any of them? So why is it orange? Well, seems like some of you, this is in black and white. But if you look at a color wheel, the beta-carotene is orange, not because it's absorbing orange, it's because it's reflecting orange. That's what you're seeing. It actually is absorbing blue. Before we look at the color wheel, where's the maximum absorbance for beta-carotene? What wavelength? 440? Okay, what color light is that? Visible is 400 to 800. Roy G. Biv? Which is the R, the R in?
Red.
Yeah, it's Roy G. Biv. So 440,
It's gonna be like
it's going to be here in kind of blue. It absorbs blue. So why is it orange? It's because if you take blue out of white light, you're left with orange. It reflects. You can get this information from your color wheel. It absorbs 440, which is right here. That's 430. That must be, okay, about 440 here. It doesn't work so well black and white. But you look on the opposite end of the color wheel, this is what it absorbs. It's going to reflect over here, and that's orange, if it was in color. So you can get that answer from your so-called color wheel. Question. If you wanted to create a pigment that was green, something that absorbs and it was green, What type of, where would you want it to absorb in the visible? You want it to appear green. You don't want it to absorb green light, you want it to absorb what? It's hard to tell with any color, right? Yeah, sorry, that's not good to ask because you can't tell what's green on the color wheel.
You can tell us the answer then?
I don't
It
know.
would be about in the red range, wouldn't it?
Here's one that's easier. If you wanted your compound to be violet, probably you would want it to absorb way over here. And,
I
well,
think
Yellow.
violet is yellow.
Yeah, it'd be yellow, because you can tell what's yellow on the wheel.
okay,
And you know violet's 400,
yeah.
so.
Forget those questions. It's hard to do without having color up there. Forget that, sorry. Okay, let's see if we can answer a pretty straightforward question here. Rank these in order from highest to lowest lambda max.
1, 2, 3, and
Which
like
would have the highest?
the one on the right.
Somebody says one on the right. Anybody say something different? What are we really looking for here?
Conjugation.
What would move it to the highest? Highest means not the highest intensity, it's the highest or longest wavelength. That's what the higher means. It's really the longest wavelength. Higher number. More conjugation. That's really the question. Which one's most conjugated?
Alright.
This one, 3 double bonds conjugated. Okay? Which one would be lowest lambda max?
On the left.
The one that's least conjugated. Which one's least conjugated? Well, the left. Because at least this is 2 double bonds conjugated, 3 double bonds conjugated. None of those are conjugated. So you don't get the narrowing of your HOMO and LUMO. Question, if I told you that two of these were colorless and one of them was pale yellow, which one would be pale yellow? Which one would be the one pale yellow?
The one on the right.
All right, because it absorbs,
Visible.
more likely to absorb into the visible. If I'm telling you two are colorless, that means 2 do not absorb invisible at all. To be pale yellow, it has to absorb into the visible. By the way, that makes sense. Because usually the first color you see for a compound it tends to be kind of yellowish. That means it's starting to absorb, so that makes sense to me. If you absorb violet, you're going to be yellow. It must be the opposite on the color wheel. It seems like it'd be red, but yeah. So that's a typical question. Down here, which compound in each set will have the highest lambda max? This looks familiar. This is transtylbene and the dibromide. Which would have the highest lambda max? Transtylbene, because here the double bond conjugates the whole system. It's conjugated. When we brominate it, we no longer have p orbitals, and we break the extended conjugation. What color was your dibromide when you recrystallized it?
It's like orange.
No. What color was your
Oh,
dibromide
it's just white.
Oh.
when you recrystallized it?
White.
It was snowy pure white,
Yeah,
which that's basically colorless.
yeah.
Okay.
When you melt it, it's colored.
Okay. What color was transtylbene? Now, you may don't remember when you weighed it out. It's not pure white. It's got a tinge of yellow to it. It's because it's probably absorbing a little bit into the visible because it's got the extended conjugation and the narrowing of the HOMO and LUMO. Where have you used UV light this term, semester? TLC identification. But when the spots show up under UV light, that's actually the spots are absorbing the UV that you're shining under. Now there's also a dye on the plate that helps the color. But something like cyclohexane, you're not going to see it on a TLC plate. There's two types of light on the UV lamp, shortwave, long wave. Okay? If you look at the lamp, it'll tell you what the wavelengths are. The short wave is probably about 250 nanometers. Long wave is probably in the 300s. This is nothing but sigma bonds. This is below 200. So it's not going to absorb like a 250 at all. So you won't see this. To see something on the TLC plate, it has to have a little bit of conjugation to move that absorbance to the right. Something like a benzene ring or a couple of pi bonds. And when you did TLC, you had some aromatic rings there with lots of pi bonds. Let's try to finish this up. By the way, this is just another look at the HOMO LUMO. Could have showed this earlier. It's really just an extension. We did these two. If you put another double bond, it gets, shorter gap, smaller gap, more, smaller gap. 1, 2, 3, 4. Imagine 11 double bonds like beta carotene. The gap gets real narrow and real easy. A couple of miscellaneous things, and then we'll give a take-home message. Indicators. You've seen indicators where maybe one's colorless and then another is colored, and they can go back and forth depending on maybe pH or something. Okay, what's going on here? It's just two different forms, and depending on the acid or base, it can exist differently. This here, this indicator, under acidic conditions, it's colorless. No visible absorbance. Under basic conditions, the molecule exists like this, and it has extended conjugation. This has a p orbital. And all these p orbitals are conjugated. But in this form, that carbon doesn't have a p orbital. And so the extended conjugation is not there, and it's actually colorless. Lots of conjugation. The lambda max moves into the visible, and it actually appears colored. You can maybe look at that mechanism, but that's a consequence of what we're talking about there with indicators. I'll let you look at this on your own. Maybe we'll look at it tomorrow. Why lower? See if you can maybe answer why is this one lower. Here's a couple of actual real-life UVVis. Please look at these lambda max. Consider the lambda max for each compound. Why one's different than the other. We'll look at that tomorrow. Last thing, application. You ever seen sunglasses that darken when you go outside? What? Yeah, transition lenses. What's going on? The lenses have compounds in them. And in the presence of light, the molecule will undergo a reaction. Back and forth. This is an equilibrium. If you got a lot of light, it will exist one way, and it will actually darken the lens. So if there's low light, the equilibrium will go the other way, and then it'll get a change. A lot like an indicator. It can go back and forth. But you actually got chemistry going on in your lenses. Let's look at that and see if there's any questions. We ran out of time here. We'll sort of sum it up tomorrow first thing. Then we'll also tomorrow, we'll look at radical reactions, radical halogenation. See some of you this afternoon, guys. Have a good day.
Ready? One more week, bro.